Now I'd like to introduce to you Dr. Bruce Barshop. He is a clinical geneticist. I think you all may know him. He's the lovely gentleman and his team who do this, the WBC testing for our kiddos and adults with cystinosis. In fact, Dr. Barshop is how I found out Hadley had cystinosis. I was very impatient and waiting for the test results, and so I emailed him, and he did inform me right as they released to our nephrologist that she, in fact, did have cystinosis. So he's going to speak to us about the intracellular cystine measurement and what is normal.
Good morning, and thank you. I'm glad on that occasion that I did answer my email. I can't commit any longer. I'm going to try to figure out how this works. What is normal? Well, normalization, Jerry Schneider was more than normal. He deserves to have his picture shown. He's been mentioned several times. Of course, he really was one of the discoverers of the underlying mechanisms, and he was the first to use cysteamine clinically, and he was also the first to develop a kind of a way to monitor the treatment and make the diagnosis. And that involved a methodology to prepare mixed leukocytes. So for years, that was the standard. He had a peculiar way. It required a specially cloned and expressed bacterial cysteine binding protein that is no longer available. So we had a giant batch of it when I became involved with him around 2007 when we merged our labs. And it was basically a radioimmunoassay with cysteine and this bacterial protein. And then, so we moved the entire project to a new platform, tandem mass spectrometry, using deuterated cystine as the internal standard. And that enabled us to really increase the throughput, and I also computerized everything, so now we know exactly what's going on with each patient and can sort of organize our results. And this is how the testing went. The blue represents the test volume for the traditionally prepared tests, the Schneider method. That required somebody to spend some time, not too complicated, but got to spend like a half a day on 1, 2, or 3 samples, and had to be prepared freshly on site at each, mostly university medical centers around the country, and then sent to us frozen. And that was what the blue test was. The orange was in 2015 or so when we started to introduce the isolated granulocytes instead of mixed leukocytes, and I'll explain more about that. The gray on top is a new mechanism to increase availability. I mean, the granulocyte test enabled people not to have to go through a whole prep on site. They could send living cells if it was sent to arrive on a Tuesday through Friday through FedEx or other express mail system. And also through I gotta say, the gracious commitment of Horizon, now Amgen, there was support for patients, both to help them find testing, get them the shipping equipment, arrange a blood draw in a local Quest station, and cover financially. So this really opened it up, and we kind of plateaued out initially. There's some increase, we keep track. There are more people who come back for testing after years of never having been tested, now that it's more available. But I think we have a pretty good coverage, and so it's running, perhaps 200 tests a year among all those things, different modalities. And there's still a few people who prefer the good old reliable, if it ain't broke, don't fix it method, if there's somebody who can perform the white cell prep at their site. But I think there are advantages to the granulocyte testing, or some specific cell type. Granulocytes have most of those granules, the the lysosomes that store cystine. So that made sense to us. But we're interested in looking at other cell types as well. And so this is some of the advantages of the granulocytes as opposed to mixed leukocytes. I don't know if I'm preaching to the choir but the thing is that it's a much more specific product, a homogeneous preparation when we isolate the granulocytes, and we just do it immunomagnetically, so we don't have to do density gradients, and it's roboticized, in fact. We have a machine that can process 4 or 5 samples at once, and unsupervised prepares these very nice preparations that are, all one cell type. This is whole blood, and mostly red cells with a few white cells scattered. This is after a conventional prep. There's a background of non-specific protein, platelet-derived proteins, plasma protein, but these multiply washed, immunomagnetically purified granulocytes seems to be a better target, and so we've stayed with that. Also, the mixed leukocyte, we had trouble with this. I mean, this is what I'm asking, what's normal? For years, it was assumed that a level of 1 was a good therapeutic target for treatment with cysteamine in cystinosis. And it's true, although they also said that for the extra renal complications, levels of up to 2 on those old tests were beneficial. But the fact is, it was chosen from a perfectly reasonable but rather completely arbitrary level of 1.0 when they went back retrospectively and looked over their data. So there's nothing magical about 1. But when I came up with this new test that didn't have a 1, it was, it wasn't scornful, but of course it changed everything. People didn't know what to think. So this test with isolated granulocytes could be distinguished. Instead of just choosing a number, I decided to choose the +3 sigma level, the level above which none of the asymptomatic carriers, the parents mostly, the level above which none of them had it. So if you could bring down a patient's level into their parents' level, that would be a reasonable and logical target. But unfortunately, it didn't come to 1. It came to something like 1.9. Also, how did that exactly correlate to what everybody was used to? Now we're measuring nanomoles of cystine, but in one case, it's that mixed leukocyte prep, and the other it's a pure granulocyte preparations, and it should be directly comparable if the protein content were the same, but it isn't. So this is the level if they were equal 1, this dotted line, that's a slope of 1. This is the best fit, and it comes out to a slope of about 1.9. It is kind of fortuitous that they came out to be the same, rather the 1.9 for the cutoff of the heterozygotes, and 1.9 for the relationship to the protein. So it was tempting to just say it was 1, just to avoid controversy and confusion. But we know this, the problem is protein. We can measure cysteine very well and with great sensitivity and precision, but a protein assay is still kind of 19th century stuff that we knew since early work that if you just made a preparation of the same 1 milliliter of blood from which you could measure exactly the same amount of total intracellular cystine, that if you put that milliliter of blood in a heparin tube, a green top tube, or EDTA purple top tube, you get a different protein. You get the same cystine. So, that's a vagary of the protein assay. The other thing we know is, so not only does the state of the sample change the protein, but but also if you use a Lowry assay or a BCA assay or a Comasi assay, you get a different result. And this came apparent during the 2012 study that was a pivotal study for the approval of what became ProCysB, that when they moved it to a CRO, a contract research organization, giant laboratory, they were getting different results, but they were using the BCA, bisinchanic acid, assay for protein instead of the Lowry that we had used, and they wouldn't change. So instead, what became Raptor, the pharmaceutical company that was developing it, published a scientific, valid fudge factor to relate the results of the results of their BCA-derived intracellular cystine level. I mean, they had to relate it to 1 because that was in the literature and that was the target. So they came up with this factor, and basically shows that there was about, I mean, you would have been off by 50% or more if you just reported that result. So not only does the protein differ depending on the protein assay result, differ depending on whether, how you prepare the sample, which protein assay you use. But even if you use just one protein assay over a mixture of different types of proteins, you get different curves. This has been known but ignored. Everybody talks about normalizing to BSA, bovine serum albumin, and that works when they're doing proficiency testing for cystinosis diagnosis through the ERNDIM system. That's a proficiency test organization from Europe. They send around one sample for protein and one sample for cystine, and everybody gets it right because the protein is always BSA. It's not the complex protein that you get from a preparation that whichever method you used was going to be different from lab to lab. So, depending on whether, what you're assaying has more, mostly they vary by glycosylation. So depending on what's on the surface of all those millions of cells that's in that little pellet that you prepared, you're going to have a different overall protein response. So protein is, well, the other thing about protein assays is that we can't do them on the samples that we really want to study, which are like single cell things and intracellular groups of cells. We can select the cells, we can measure the cystine, but we have no way of normalizing. So what is normal? This is the problem. So preparation is different, the composition differs. Think about the complexity of the protein mixture in a sample of blood from one person, from that person on another day. How about that person after a stem cell transplant? What do you think their cellular protein compositions are going to give you? And how does that relate to bovine serum albumin anyhow? So we thought much more logical to normalize to a specific lysosomal protein. And we tried this. We sort of showed it could be done using proteomics back in other earlier studies, also supported by the CRF. Starting with that observation that the apparent protein that you get, and the final result of cystine per milligram of protein between EDTA and heparin varies. So we thought maybe we could use a new method. That would be something to test if it's sort of agnostic and we get the same ratio to something. And so we did a basic proteomics search and found 3 proteins out of more than 180 that we could identify the proteins perfectly with perfect confidence. And we prepared stable isotope analogs of those peptides, and we sort of did a quantitative, semi-quantitative proteomic experiment. And it worked in principle. I mean, it did improve the correlation, but it's hard to do. It would be very expensive, and there are plenty of ways things can go wrong with these presumably quantitative proteomic experiments. I mean, it takes days. You have to break down into individual peptides. You have to have some controls to make sure that you're breaking down every susceptible lysine, if it's trips, that you're making your peptides quantitatively. It's not easy to do in a quantitative way, and there aren't any really, I don't think there are any clinically approved quantitative proteomic tests yet. So we had to look for an alternative to that. So we can, we have a way of using a fluorometric plate reader. We can measure quantitatively quite decently concentrations of, for example, LAMP2, which we're furthest along. We're also looking at vimentin and thinking about using that to pull out living renal tubular epithelial cells from urine samples. We're looking at other markers, surface markers of the lysosome, even also thinking about trapping intact lysosomes and looking inside of them, for example. But for the clinical testing, the thing is, we're starting to do this and we're collecting the data, but I want to warn you and I want to ask your help because we do think that finding an lysosome-specific biomarker quantitation would be the best way to normalize. But we're going to be left with we're going to be left with a new ratio, nanomoles of cystine per picograms, or we'll probably scale it up, nanograms of LAMP2. So we don't know what, I mean, we're going to have to be running them in parallel for years, I guess, to see what kind of correlation there is. And there's likely also to be this imperfect correlation because one of the measurements is imperfect. I mean, we know that protein assay is going to have some wobble. So it's going to be a complicated future. And I want to warn you about that and ask for ideas for how we can convince ourselves that this ratio is, valid. The last way took 10 years, so we may have to do that with, retrospective analysis of how patients did it. And I don't want to wait 10 years. So, I want to move ahead with this. And I solicit your advice and patience and approval. Thank you very much. I think, thinking about what would be a good monitor, trying to think of a tricorder. But thanks so much. How did I do on time?
Thank you, Dr. Barshop. We have time for some questions. Okay, Sergio.
Very nice presentation. For clinical testing, in my opinion, I wouldn't use a lysosomal marker because you have an increased number of lysosomes, you are going to have increased number of cystine, and then you are going to correct, and that ratio will correct to a number that is arbitrarily low through, and also I think that isolating lysosomes or looking for those markers is going to be time-consuming and introducing error. But the question is, why don't you express just cystine levels by the number of granulocytes? Because at the end of the day, isn't what you care about is the level of cystine per cell? It's just counting the cells. Because you are isolating to purity now, right?
Actually, I appreciate that. I think that's a good idea. We now have markers to do that. We have to just sort them, essentially, or quantify. There are simple cell counters. So I will add that as well. But still, yes, that would be another new number that we're going to have to propagate into the future and then correlate the ratio to what we accept to be a clinical indicator, which is per milligram of protein.
And one more comment, if you are going to pick up a neutrophil protein to normalize, I will pick up myeloperoxidase. I didn't see it on your list. It's the most abundant. It's 5% of the dry weight of a neutrophil is all myeloperoxidase, and it's the easier to basically pick up in Westerns and stuff.
I appreciate that. We're ordering antibodies every day. So I don't know, we might have already had myeloperoxidase. I think we just had the best success with this so far, LAMP2.
In your last slide, you talked about measuring this assay or something in urine voided by the patients, and so you'd get direct access to urinary tubular cells. So if you're not a transplant, that seems like a really direct way to sort of deal with that. Is that something you're actively pursuing?
A priority, in fact, of mine, yes. And we collected urine just yesterday that'll be used to look at that. We've used different antibodies to pull down cells. There's a lot of nonspecific things. We've known for years that you can find enough, they're continuously being shed, renal tubular epithelial cells. You can easily recover enough of them to culture out, but we want to just look at those existing cells and their cystine content before they culture out.
Yep.
So that requires incredible sensitivity of protein determination, for one thing you can imagine, but it's also a process that we're optimizing, finding the right antibody marker and so forth. But we're looking at it. That should give the instantaneous, maybe the most important disease burden indicator, I would think, in a pre-transplanted, untransplanted patient. And more or less an instantaneous thing, and maybe less susceptible to I know I'm getting a blood level, so I think I'll take my cysteamine for a couple of days phenomenon. It may be just as susceptible, but I doubt it. So we're going to look.
I'm making a guess here, but the patients probably would prefer it to the rectal biopsy.
Oh, yes. Well, the rectal biopsy, I should say, isn't as bad as it sounds, but also it's not, for me, not as useful. It's funny, the crystal count data does seem to show trends, but the cystine content of those biopsies, there's a problem because even across one biopsy, there are wildly divergent results in actual cystine. And I think that in a tissue that's not so quickly turning over, at least, that when the cells die, the cystine that was inside of those dead cells and dead lysosomes isn't just going to disappear. So there's extracellular lakes of cystine, I think, in such tissues, except for the most rapidly turning over, perhaps. But that's another area we're interested in investigating, yeah.
Ladies and gentlemen, you just witnessed a mini scientific symposium. Are there any other questions for Dr. Barshop?
Yes, so.
Okay, thank you so much.